So I was instructed to try and explain or try and motivate what role quantum mechanics has played in the development of mathematics. Now, I neither have the expertise or the courage to actually review this topic in its entirety. So I intend to actually convey to you some of the excitement that I have been personally involved in. So this this cartoon actually gives you a part of the story that quantum mechanics has played in the development of mathematics. There is the beautiful review that you heard in the morning about how string theory has developed and how in its turn it has actually contributed to the development of certain aspects in mathematics or certain understanding better certain aspects of mathematics. My viewpoint in this talk is echoed by something that Freeman Dyson and Wigner and Penrose have very articulated in several of their writings. So Dyson, paraphrased, says the mathematics that has been developed for its own sake, for the glory of the human spirit, has always found unexpected applications to the physical universe. And Wigner and Penrose have echoed that mathematics has the uncanny power of anticipating the physical world. So at various stages of your research career, you sometimes question your life choices, and then sometimes when you are not in a very good state of mind, you look at or you try to draw inspirations from big people who have contributed to the development of science. And so this actually nicely reflects sometimes my mental state of mind when I embark on certain research directions, which typically are doing some random walk in theory space. Now, although mathematics is going to be the motivation behind much of what I'm going to describe, there is also going to be a connection with physics, and the physics motivation and connection should be simple. And it should be as simple as what was echoed by Sidney Coleman, where he said that the career of a young theoretical physicist consists of treating the harmonic oscillator in ever-increasing levels of abstraction. So even there is going to be some role that string theory is going to play in my talk, but it is going to be at the level of thinking in the language of the simple harmonic oscillator. So the question that I'm going to start off by asking is, what is pi made of? Now, pi with an E at the end is made up of a lot of things, and is made up of, I don't know, this is probably a blueberry pie, there is some pecan pie or something, and so it's made up of a lot of stuff. So the answer to the question here is also going to be that pi can be made up of a lot of stuff, but what do we mean by this lot of stuff? So from the perspective of physics, what does what pi is made of even mean? So let's start by discussing the first ever infinite series representation of pi, which is called the Madhava series. It's also called the Madhava-Leibniz series in the West. So this is an artist depiction. If you Google Madhava, you will find an artist depiction of how confident Madhava was because of all the mathematics that he invented. He belonged to the Kerala school of mathematics. It's fascinating as to how he wrote down this infinite series. So obviously, these notations had not been invented in the 14th century, and this was also pre-calculus. So in fact, his series was explained in the form of slokas. So you can actually do an internet search and figure out how that slokas translated into precisely this. And it's not just this series that you see here. He was able to also calculate the remainder term if you truncated this series up to a particular order. So it was actually quite a remarkable set of achievements. Now, this series, especially for the students in the audience, is what is called a conditionally convergent series. And there is something called the Riemann rearrangement lemma, which tells you that if you rearrange the terms in the series, you can make it to converge to whatever you want, not just pi, you can make it to converge to 500 as well. So the fact that this converges to pi has to do with the canonical ordering of the series. Okay? And I'm going to tell you that this series belongs to a family, an infinite family of series of formulas of pi, which actually arises by thinking about certain problems that were motivated by string theory. So the first thing is, my contention is that this n that enters the formula actually tells you how fast the string vibrates. It corresponds to the mass level of the string state. I'll make this more precise in what sense this is the mass level of the string state. So you have an underlying picture where you have this vibrating string. Now if you spend a couple of minutes looking at this picture and various imageries start popping in your mind that, okay, so this is something like a rubber band, maybe it's rubber band wobbling or something like that. And the first thing that comes to your mind, if you're not a string theorist but actually a realist, the first thing that comes to your mind is the rubber band has an elasticity. So where on the hell is the elasticity parameter in this series representation? And the other thing, mathematical fact that you should know is that this canonical form is notoriously slow to converge. In fact, if you actually keep adding the terms, even to get 10 decimal places, you'll require billions of terms. Now, in order to make this connection between the Madhava series and string theory more apparent, I need to tell you about what is called the Euler beta function. So Euler should serve as an inspiration to any academic, because Euler invented a huge amount of mathematics. So he actually popularized the notation pi. Now when he was thinking about pi, he thought of pi as twice the value that we are familiar with right now. So pi became 3.141 later on historically. But he invented the notation E. Sometimes this for high school students is sold as the most elegant formula, most beautiful formula, because there is imaginary number E, pi, and yet somehow they conspire and become -1. He invented the Euler beta function. This is the Euler gamma function. This is the Euler zeta function. But remarkably, so this is Euler. He actually went blind towards the end of his life, and if you stare at this figure a little carefully, you can see that he's squinting on the right eye. So whenever this portrait was painted, he had already started having problems with his eyes. For some reason he's wearing this weird headgear. I don't know what that, maybe he just came out of his bath or something. But anyway, he went blind towards the end of his life. He lost his house in a fire. His wife died, but his productivity increased. And I can assure you that this productivity increasing had nothing to do with his loss of wife. I mean, I'm pretty sure that his productivity was anyway, it would have been quite astonishing. What? Yes, it was fine. My wife has heard this joke before, yeah. So he produced so much mathematics, so he produced 25,000 pages of math, and his work continued to be published 50 years after his death. Now I'm not saying that you aspire to produce 25,000 pages of whatever you're doing, but then this serves as an inspiration that if somebody like Euler, who with his handicap could be so productive, and this was also in many sort of 300 years back, he had scribed, he was inventing mathematics in his head, and his scribes used to note things down. I mean, there's no reason why you shouldn't succeed. Okay, so this Euler beta function plays a role in string theory. It is the simplest scattering amplitude that you're going to see in string theory. The reason why pi enters is that if you take the Euler beta function as it stands and substitute x to be equal to half, you actually get pi. So to get an infinite series, you'd require to find an infinite series representation of this Euler beta function. Now I'll just do my sales pitch before I tell you the actual story. The sales pitch is that we discovered, and by we, this was building on a lot of work, and part of the work was actually involved ex-students from IMSC. So one of the work that I'm going to talk about is with Arnab Saha, who was a student in IMSC. It was published last year in Physical Review Letters, and it was also selected by Scientific American as one of the 7 coolest mathematical discoveries of 2024. And whatever I'm going to report, the mathematical aspects, has an alternative proof by mathematician Hjalmar Rosengren. And so mathematicians, of course, the way that they function is that they look at something that a physicist has produced and say that we don't understand it. We are going to find our own thing, which is going to be more rigorous than what you have done. And so they ignore whatever you have done and they find their own thing, and to sort of prove to a physicist that you are not rigorous enough. Okay. So anyway, we discovered an infinite number of new formulas for pi. And why infinite? Because in the picture of the vibrating string that I showed you, I was asking where is this elasticity, and so there is going to be a parameter that is going to be there in my series representation, and that parameter you can choose to be whatever value you want, and that is how you are going to get an infinite number of new formulas. But I should actually point out that pi was not the main focus of our work. My sales pitch is actually selling it in a different way. The main focus of our work was completely different. I'm going to explain to you what the main focus of our work was. But it was an outcome. In fact, we debated, Arnav and I distinctly remember we had this debate whether we should just push this formula for pi in the supplementary material, in which case it would have been completely ignored. But somehow, for some good reason, we put it in the main text. So after we discovered this formula, we presented our results to mathematicians, and the mathematicians asked us if Ramanujan's famous work on 1 over pi series also has a physics interpretation. Okay, I will tell you about Ramanujan's 1 over pi series. And so the second part of the story that I'm going to tell you, we embarked purely driven by this curiosity that motivated us because of the question that mathematicians asked. The first part of the story that is going to actually give you this new series representation for the Euler beta function, we were asking a question motivated by string theory. This had no such motivations. We were actually trying to figure out where or how possibly there could be some connection of that kind. So the first version of this paper appeared earlier this year with my graduate student Faizan Bhatt, and under the title Logging the Conformal Life of Ramanujan's Pi. So the title will give away the story. We found an interesting connection with what are called logarithmic conformal field theories and these Ramanujan pi series. So this is Ramanujan's pi. This was written in 1914. So historically Ramanujan went to Cambridge in 1914. He reached Cambridge in April. And this paper got published later on, so clearly he had been working on it. I think he had done most of the work in India, and then he got it published when he was in Cambridge. And so this is, so in his paper there are 17 such formulas. There is nothing sacred about these 17. There is no physical reason or mathematical reason why the number is 17. But he wrote down 17 such series formulas, and these are amazingly fast converging series representations. And if you stare at it, I will explain this notation. This is a Pochhammer symbol. So it is a version of the factorial function. I'll define it in the next slide or a couple of slides later. But you see this weird looking factors. There is 99, there is 9801, 9801 is 99 square, and these numbers appear. And you know, these are really weird, and you begin wondering where these formulas come from. So these are very fast converging formulas, general proofs, because Ramanujan was very concise in his writing. He never gave any intermediate details. There's a reason for it. I'll explain the reason later on when I actually talk more about it. But these formulas, there's a book written by the Canadian Borwin brothers in the 1980s which explains where these formulas come from. And these formulas form the basis for modern techniques to calculate trillions of digits of pi. I don't know how many of you are fond of pi, but then the world record right now is 200 trillion digits. Now you would wonder, why would you actually require 200 trillion digits of pi, for what purpose? Except for showing off to your friends and for memorization purposes or some quantum computer science purpose that you have algorithms that converge fast. So let me ask you, so suppose I asked you how many decimal digits of pi do you actually require? Suppose you wanted to describe the observable cosmological horizon to Planck length. So what precision or how many decimal digits of pi do you think you'll require?
10 to the 30 with lambda over m. 10 to the 60.
You just require 60 decimal places of pi. 60 decimal places of pi, exactly. You don't require more than that. So anyway, of course, because it's Ramanujan, there's a romanticism associated with Ramanujan everywhere. So in fact, these formulas, the first two formulas have appeared in a Hollywood movie as well. You can find out about it. The Hollywood movie is named High School Musical. And of course, you know that there is a movie, there's a book written on his life. And there is some interesting question. So somebody speculated that suppose Ramanujan had access to some software like Maxima. Now I am thankfully not a dinosaur as yet, because I've never worked with Maxima, but it was before my time. But if he had access to Mathematica, ChatGPT 5, what would he have done? Now maybe it would have gone in the other direction. So maybe he would have not discovered any of this. And so it's fascinating to speculate what happens to creativity in light of these computer packages. So this work is going to be based on some of my work which builds on other people's work. I will refer to them as time goes on. So the names in green are people who are associated with IMSC. So this Arnab I've already mentioned. Prashant Raman was also a student in IMSC, and there is going to be an important part of the story where he played a role. And I should actually say that it is not as if we suddenly decided, oh, it will be so cool to find a new formula for pi. That is not how the story progressed. We were rather building on things that we were developing over the last 10 years. And this line of research originated from exploring critical phenomena. So we are calculating critical exponents in associated with Wilson-Fisher fixed points. And the first the actual papers which motivated us along this direction were these two. Okay, so the pi punchline is that there are infinitely new formulas for pi. So let me just show you. So if you take the open superstring, the new formulas actually look like this. So the starting formula, so starting is 4. So there are corrections or large corrections to 4 that are given by this. So even in the Madhava series, the first term is 4, and then you get an infinite set of corrections. So the new element here is that there is a parameter here, lambda, which I would like to interpret it as the elasticity parameter that is associated with the string or underlying string picture. And then there is a Pochhammer. So what is a Pochhammer? So Pochhammer is the rising factorial. So a subscript n looks like this. So basically it is a degree n polynomial of this argument a. It is called the rising factorial. So if a was 1, you get the ordinary factorial. In this formula, lambda could be a complex or a real number as long as the real part of lambda is bigger than -1. It's a free parameter. You can choose whatever you want, and it is going to always give you pi. So this formula does not exist in the mathematics literature. This has been confirmed by mathematicians. And how you recover the Madhava series is the following, that if you set lambda to be very, very large and you truncate this sum, then each term in that summand is going to approximate to the Madhava series. Okay? Except there is a subtle difference. This series is absolutely convergent, unlike the Madhava series, which was conditionally convergent. So the tails of the two series, of the Madhava series, and the tails that appear after doing this large lambda limit are going to be different. So this formula interpolates the Madhava series to a faster converging quantum field theory or string theory inspired one. So as an example, let me just show you a few things. So I should credit my new graduate student CGPT the 5th. So now CGPT can actually is reliable in doing numerical calculations, unlike its lying brother, the CGPT the 4th or the 3rd. So for example, if you set lambda equal to 8, it need not be an integer, it could be whatever you want. And you consider 9 terms, then actually you get an agreement within 10 to the power minus 7. And this is what the series looks like. For lambda equal to 13, it looks like this. And the agreement is within 10 to the power minus 7 for these. Okay, so this is just to give you an example what advantage you have in using this extra parameter. So the next part of the story, so this is still continuing with the sales pitch, is the story about Ramanujan's 1 over pi and the conformal field theory. So the take-home message is that these kind of series representations, the origin of the series representations, have something to do with the black hole membrane paradigm. So the way that you calculate transport coefficients uses this picture of the membrane paradigm, and I'll explain to it how it is connected to the membrane paradigm later on in my talk. And from this picture you get even weirder looking formulas for pi. So for example, 1 over pi has this approximate formula where you start seeing logs in the formulas. And one of the reasons, underlying reasons why you see logs in the formula is because these bizarre looking formulas come from log CFTs. They are a special kind of CFTs. These are non-unitary CFTs. These CFTs actually have to do with percolation, turbulence, things like that. So these are not the run-of-the-mill CFTs that you're usually familiar with. These are the kind of CFT that I'm going to, or that played a role in my story, is a C equal to minus 2 CFT, which is a theory of the symplectic fermions. So, and then I should tell you, and this is because Sandeep is there in the audience, there is also a surprising connection with 1 plus 1 dimensional de Sitter space. Okay? So you solve the Klein-Gordon equation at 0 frequency in 1 plus 1 dimensional de Sitter space, and you write the de Sitter space in the static patch. You calculate the Green's function with regularity at opposite horizons. The static patch has 2 horizons. And the Green's function is precisely the combination of 2 F1s that goes into the beginning of these Ramanujan type identities. Okay, so this suggests a nice physics route, maybe in the language of this so-called double-scaled SYK model, in trying to address the question, what is pi made of? So let's get going. So, and then now you're thinking that why are we talking about this problem? So what motivated us into reaching this point? So why? So I could remind you of the quotations that I showed you in the beginning by Dyson and Wigner and Penrose. But the real answer is that in a large part we were trying to reimagine the origins of string theory. And the reason why we were trying to do that is because we now have new tools at our disposal, namely new ways of thinking about the old bootstrap problem. Now, Bala Satyapalan is there in the audience. I'm pretty sure that you are aware of how string theory originated by solving the bootstrap equations, and Sandeep of course is also there, but I'm just ordering them in the order of age because the probability that Bala will know is higher. So let me just give you a brief history of early string theory, and this is before the kind of string theory that Sandeep reviewed. So string theory originated by a spectacular guess by Veneziano. So there were multiple people who were trying to actually come up with a guess for this scattering amplitude. So there was this program which was called Chu's bootstrap program. Chu was Geoffrey Chu, who was in Berkeley, and he had famous students working with him. One of them was David Gross. So David Gross actually was given the task of trying to find out something like a Veneziano amplitude, and he is still to date bitter that Veneziano beat him to it. And so Veneziano came up with this Euler data function, and it turned out to be a consistent kind of amplitude to describe 2-to-2 scattering. And the motivation behind trying to do this was to understand pion nucleon scattering. The motivation behind trying to come up with these amplitudes wasn't a theoretical one. It was actually driven by experiments. Then remarkably, and this is something that I find extremely fascinating, and after I got very interested in the history of string theory, this was pre-internet days, and the rate at which the field developed was spectacular. Because within a year, these 2-to-2 scattering amplitudes were generalized first to 5-particle amplitudes by Bardacci and Reg, and then to n-particle amplitudes by Koba-Nielsen. And this was a very important development because it made perturbative calculations possible at loop level to check the unitarity of the theory. The reason why you get d equal to 26 is because of the unitarity conditions that you get by calculating loop diagrams. Then later on in 1970, the world sheet picture emerged. So this was purely based on these developments. People did not realize that there was an underlying harmonic oscillator picture which was associated with the quantization of the fields on the world sheet. That realization came soon enough, and that was attributed to Nambu. He actually very generously admits that he never published this. He actually gave a conference proceedings. So if you ever come across a book, The Birth of String Theory, which was published around 15 years back, and Nambu reminisces, and he actually says that he didn't even make it to the conference, but he had a write-up, and it was somehow it made it there, and then somehow his name got associated with this world sheet action. So then Susskind also reminisces in the same book, and then Nielsen, and they realized that there was an underlying world sheet picture. But after a frustrating few years, people failed to explain hadron scattering using string theory. So this was the original motivation to explain pion nucleon scattering data. So they gave up on this because they realized that they couldn't explain pion nucleon scattering using this original attempt. And then later on it got reinterpreted as a possible candidate for a theory of quantum gravity. This is work by Shirk and Schwartz and others. And this is what Sandeep reviewed very nicely in the morning. Now, my interest in old string theory stops here, and I'll begin to tell you about some folklores. So there is a folklore in old string literature, and I will prove it to you by showing you snippets, quotations from very well-known sources, that it is very different from quantum field theory, and one of the reasons why it is very different from quantum field theory is because of this picture alongside. Now imagine that you are doing point particle scattering, 2 to 2 scattering, so this is called the S channel diagram at tree level, and this is called the T channel diagram at tree level. You fatten up these lines, so if you fatten up these lines, the string version will look like this, and if you fatten up this line, the string version is going to look like this. But this picture is suggestive. If you stretch the top picture vertically, it will become the second picture. So in that sense, string theory seems to suggest you don't require to add both channels. Just computing one of these diagrams is enough. This other diagram is already inbuilt from the string world sheet point of view. So this old literature is filled with statements that unlike quantum field theory, string theory, you don't have to add channels. But this statement is wrong and misleading. It is misleading because string field theory makes it very clear that a Feynman diagram as picture is indeed possible. And this is important because I'm going to soon start talking about the way that people were actually looking at how to solve the bootstrap problem before string theory came into the picture. They were working on solving a consistency program called the bootstrap using representations which were non-perturbative. And the question that I'm going to ask is that do these representations have some kind of a string stretchiness while admitting this decomposition in terms of the Feynman diagram picture? Okay, so it's a non-trivial problem because you would have thought that either you have the Feynman diagram picture or the string picture, but not both at the same time. So by a dispersion relation, just to tell you immediately, we mean the following. So if you have 2 to 2 scattering, then there are 2 Mandelstam invariants. I will make it more precise in a bit, but then basically the amplitude, scattering probability amplitude, is a function of 2 variables, Mandelstam invariance S and T, and you want to do something like a Cauchy formula. The way that we think about Kramers-Kronig dispersion relations in electromagnetism, we want to write down a formula of this kind in terms of just the discontinuity of the function. So this is just a version of Cauchy's formula, and there are ways to spruce it up. But basically when you write a formula of this kind and you're doing it for a function of 2 variables, you have to hold one of these variables fixed. So this, as I'm going to review in a few slides, is what is called the fixed T dispersion relation and forms the bread and butter of anybody that is working in amplitudes with the dispersion relations.
Sorry,
yes.
Is a complex,
yeah, so you can think of S and T to be complex variables. Yeah, so and you're holding T fixed, and you get a formula of this kind. This is just Cauchy's theorem, provided that the arcs at infinity die off fast enough. So there are some restrictions, so the amplitude has to die off fast enough. So the answer, so the question was that is there a representation of this kind which actually has both these pictures, the string worldsheet picture as well as the decomposition in terms of Feynman diagrams in the representation itself. Okay, because the idea would be that once we have such a representation, we could go back and reimagine what the bootstrappers of the 1960s could have done with such a representation.
sorry, one more. So there an S channel Q squared is positive.
Yeah, no, so yeah, okay, so T is negative in the S channel, and the opposite is true in the T channel, yes.
And that does not relate them?
So the question is that when we write down a representation of this kind, then because we are holding T fixed, if you have a function which has poles in both variables, you're not going to see the poles in the T variable. So the challenge is that whether there is a formula which makes manifest all the poles while admitting this kind of a decomposition. Yeah. So just to convince you, so this is Green, Schwartz, Wheaton. At least I learned string theory from Green, Schwartz, Wheaton. This is a famous textbook description, and somewhere in the introductory chapter they write that the duality hypothesis, the fact that this was the same as this is called a duality. In modern parlance we call it the world sheet duality. There are various kinds of duality in string theory. This is called the world sheet duality. The duality hypothesis never had more than a slender experimental support, and this slender experimental support is based on an earlier paper before the Veneziano amplitude came by Dolan, Horn and Schmidt. I will tell you exactly what Dolan, Horn and Schmidt says, because like good opportunists we only picked up the relevant portion of that paper and ran with it. The duality hypothesis never had more than a slender experimental support, and the Veneziano model was merely an ad hoc way of satisfying this not so well motivated hypothesis. Okay, so this is a very blunt admission that at least the duality hypothesis on which the early string theory was invented or based on was just something that was flaky. Yeah. So if you open Mandelstam's famous dual resonance models review from the 1970s, he makes the same claim that when you do scattering in elementary particle physics, you add channels, but if you are thinking in the language of composite narrow resonance, then the sum over poles in the T channel is the same as the sum over poles in the S channel. Okay. If you open this is a more recent textbook. This is from 2012. You will see John Schwartz talking about something called double counting. Yonea talking about something called double counting, that you should not add both the diagrams because it will be double counting. Michael Green talking about this phenomena called double counting. Okay. So these, what are the mathematical series representations that are known for the Euler beta function? So you open, so for the younger member in the audience, there used to be this textbook called Bratstein and Rizek, which was this thick. It was more than a paperweight. You could actually do dumbbell exercises with it. So you've never seen it because now all these formulas are readily available on the internet. But
Book can still be used.
book can still be used, exactly, for weightlifting, yes. And so if you open that, you'll see these representations. So one of them is this representation where you're summing over. So remember the beta function, Euler beta function has two gamma functions on top and one gamma function in the bottom. So there are poles in both the variables S1 and S2. So this is a series representation so which makes the poles in S1 manifest. For this to converge, you require the real part of S2 to be less than 0. Similarly, if you interchange S1 and S2, you'll get a series representation that converges when the real part of S1 is less than 0. This is related to your question that in terms of the channels, you require to restrict the sign of the other variable. So this is the standard representation, this is what would arise from these fixed T dispersion relations that I told you. There are different ways of deriving this. I won't go into that. There is another representation which is not frequently quoted in the string literature, which actually somehow tries to make the poles in both variables manifest. It looks like this. So remember that these are getting dressed by these polynomials in S2. The polynomials in S2 also encode the kind of spin that is getting exchanged, what kind of spin the intermediate particles carry. In fact, the fact that for a very large mass level you have a very large degree of the polynomial in S2 is indicative of the fact that the higher masses decompose into very large spin representations. This representation is what would be close in spirit to the Feynman diagram like decomposition, where you have both channels. It is again dressed by some kind of a polynomial, but again it is only convergent over a restricted range where the real part of S1 plus S2 is bigger than -1. As a result, neither of these known series representations conforms to what is expected from the analyticity property of the Euler beta function, because the Euler beta function does not have these restrictions, these kind of restrictions. Okay, it is defined without these restrictions. Now, curiously, I tried to dig up the old literature. This series representation is rarely mentioned in the string literature. I don't know why. I mean, there's one paper, just one paper I located where somebody talks about it. That paper has one citation, so obviously the people have just simply ignored it. This paper was by Nakanishi. I think it's of the same fame as Nakanishi, Lathrop in quantum field theory. But neither of these actually meets the field theory expectations, because from the field theory we only expect that for tree level amplitudes that the only non-analyticity should be at the poles, and neither of these also exhibit this elasticity property that we heuristically expect. And just to point out, Dolan, Horn and Schmidt never made a strong claim that the T channel should be equal to the S channel. Okay, this is what they actually said. So if you open this paper, they were actually looking at scattering amplitudes. They were looking at pion, nuclei and scattering data, and they said, and this is their first claim, that the amplitude should look like the sum over S channel poles plus so this is the sum over T channel poles plus sum over S channel poles, and then you have to subtract off something, and this is a phenomenological subtraction that they motivated, simply because if you did this, the amplitude value that they would have gotten is bigger than what experiment predicts. Okay? And then they make some sort of very heuristic remarks that if the resonances are sufficiently close enough, then you would average them out, and as a result of which the amplitude should be only given in terms of just the T channel poles. This is the statement that they make. Okay? It's some very sort of generic possibility. Now, in the old literature, historically, people had investigated this kind of a representation without adding the subtraction term. And without adding the subtraction term, the model that they were investigating to explain this pion, nuclei and scattering is what is called the interference model. And this interference model was trashed in those days, and in some sense people thought it was garbage. But if you look at what Dolan, Horn and Schmidt actually mention, it does seem like the authors are clutching at proverbial straws. So this I'll skip. And this is an appropriate point to actually tell you about one of my favorite quotations by Alexander Polyakov. The garbage of the past often becomes the treasure of the present and vice versa. And now I leave it open to interpretation what you want to put for garbage and treasure. Which one is string theory and which one is something else. So in the early 1970s, a very small group of people had asked precisely this kind of question that I'm asking, that if a non-perturbative representation of scattering amplitudes can be found that manifested all the symmetries, including this crossing symmetry, the fact that you require to add S and T channels in the representation. And this was the work that I'm most familiar with is by Oberson and Khoury. So this we discovered in the lockdown when we were tearing our hair in frustration with Rajesh and Ahmadullah. And in the 1970s, there is an Indian connection here. This is S.M. Roy of TIFR, along with collaborators Mahus and Wonders, had also investigated a similar question. Okay. So this line of research was largely ignored, but it was solid work. The mathematics was solid. And this is something because although I have dyed my hair, so you don't see enough white hair, I have enough white hair to actually give you some gyan that solid work is not meant to be lost somehow thanks to Inspire Help and the internet. Don't worry too much about citations. If it is solid, someone will pick it up hopefully in the future. So don't judge a paper only by citations. Please read it. I mean that is the underlying sentiment here. So just to give you some basics now to go more into the meat of the topic, especially if people are not familiar with scattering. So you're scattering 2 to 2 identical scalar particles. For simplicity, it doesn't matter. They don't have to be scalars. So they carry the 4 momenta P1, P2. These are incoming states. These are outgoing states, P3, P4. These are Mandelstam invariants. So if your external particles are massive, then S plus T plus U is 4m squared. Now later on in my slides I will use S1, S2 and S3 instead of STU, so don't get confused. So when we write down a scattering amplitude, it usually decomposes in the following form. First there is something which corresponds to nothing happening, so it is just particles going through each other, so this is called the disconnected part, the identity part of the S matrix. And then there is the transition amplitude I times m. So the I times m can be written in the following way. In this particular case, you can pull out a momentum conserving delta function and you get a probability amplitude, whatever is remaining is a function of S and T, these Mandelstam invariants. Our object of interest is this function of S and T. Okay. So what are the tools? Now again, this is going back thinking that in the 1960s, no string theory, we just have bootstrap consistency conditions. As you know, I think many of you know that the founding fathers, people like Dirac, Heisenberg, they sort of wanted to throw their baby out of the window. They didn't like the way that quantum field theory was being developed. They wanted to work in terms of observables. That is how this bootstrap program originated. The people wanted to talk directly in terms of observables without talking in the language of fields. They wanted to calculate probability amplitude directly, constrain them using consistency conditions like unitarity, crossing symmetry, analyticity, and so on. So this is imagining what tools would have been available at that point of time. So we want a non-perturbative representation of M of ST, and the tool that was used during those days are what are called dispersion relations. I have briefly introduced this already in the Cauchy sense. So the prototypical dispersion relation that you should have in mind is the Kramers-Kronig one for the electromagnetism. So what you have is you're looking at the complex S-plane, and the complex S-plane could have branch cuts because of the fact that you go into the continuum. And they could have bound state pools somewhere. And imagine that you are trying to write down a formula, a Cauchy formula for the value of the amplitude at that point there. You would actually start off by drawing a small circle here and deforming the contour, blowing it up so that it takes on this form. It wraps around the cuts, wraps around these possible bound states, and then also it gives you the arc at infinity. So if you were able to drop the arc at infinity, you would be left with a formula which would be a real line integral along the cut, and because of the fact that this arrow is pointing in this direction and this arrow is pointing in the opposite direction, instead of the function itself, you would pick out the discontinuity of the function across the cut. So that is the sense in which dispersion relations are built. The discontinuity plays a major role because unitarity statements for the discontinuity of the amplitudes are very easy to state. One easy statement is that when you do what is called a partial wave decomposition, then the partial wave coefficients have to be positive. So if you want to examine if the low energy expansion of a particular amplitude has certain positivity properties, this would be the starting point. What I have described here is what is called the conventional fixed T dispersion relation, because the amplitude 2 to 2 scattering has two variables. One of them you have to hold fixed in order to write down a dispersion relation of this kind. And then on top of this, you have to impose this restriction that M of ST is the same thing as M of TS. But this is of course not manifest in the fixed T dispersion relation, and as a result of which you have to impose new kinds of constraints. Now the reason why I don't like the fixed T dispersion relation from the perspective of the Euler beta function or the Veneziano amplitude is because of what I told you, that if we used it for the Veneziano case, then the poles in T will not be visible because you are holding T fixed. Okay? And you want a representation where poles in both variables are fixed. This means that there is a limited domain of convergence and does not make the analytic structure of the Euler beta function manifest. So we require a new kind of dispersion relation, and this is going to be the outcome of this kind of questioning. So this is a development of a new kind of dispersion relation which actually makes the analytic structure manifest. So we need to actually have an extra parameter in the dispersion relation, which you can think of as the elasticity parameter. The elasticity parameter literally does the following. It will enable you to think of the amplitude as a membrane and stretch the membrane to get the S channel or the T channel. And if you did something drastic, you can actually tear apart the diagram and then glue it back together, which will actually give you this Feynman diagram-esque picture. Here is the dispersion relation. So this is something that is an outcome of a lot of work. A lot of people have worked on it. This is Oberson and Khoury, and then with my graduate student Ahmadullah, then with Rajesh, and then Prashant. And then surprisingly, this contribution was a very important contribution. So Cha-Ming Song is a statistical physicist based in University of Miami. He has no relation to any of our fields, but he was looking, I would say, for good taste. During the lockdown, he was reading papers on the 3D Ising model and what has been done. He came across our papers, thought they were excellent, and then because of his good taste in mathematical nature, he probed further and he managed to actually improve on that. And then I mentioned the work with Arnab, and this is another much more simplistic derivation of the stringy dispersion relation. This is self-contained. You don't have to go through this Oberson-Khoury parametrization. It's just simple Cauchy's formula applied in some clever way. The dispersion relation takes the following form. The claim is, this is the scattering amplitude that I was telling you, S and T, or S1 and S2. There is a new kind of kernel. So instead of just 1 over sigma minus S1 that you see in the fixed T dispersion relation, I will add sigma minus S2 as well. And then I will add the subtraction term. The subtraction term plays a crucial role. It will become obvious why the subtraction term is needed. And the subtraction term will be parametrized by something. The key change is that unlike in the absorptive part of the amplitude or the discontinuity of the amplitude, you would have held T fixed. So you would have seen T here. You don't see T here. You see a more complicated function that appears here. The complicated function, let me just run it with you because it will play an important role. Notice that if S1 was equal to minus lambda, then lambda was equal to minus S1. If lambda was equal to minus S1, then this would simply become lambda equal to S1. Okay, this would be replaced by S1, and if lambda is equal to minus S2, this would be replaced by S2. This kind of a dispersion relation actually enables you to interpolate, depending on what value of lambda you are choosing, interpolate between all kinds of known dispersion relations that are known to us. So of course this picture is suggestive because, as you saw in Sandeep's talk, that there was a web of dualities where you see string theory, 2A, type 2B, etc. sitting at the corners, because of the fact that we are brainwashed as string theorists to thinking that this is the grand unified dispersion relation. We must have a picture of this kind where you see the various kinds of known dispersion relations at various corners, and this dispersion relation does precisely that. Now here I wanted to advertise, this is partly indicated in this work, but then more work has been done with Arnab. We have a version for the 5-particle dispersion relation, and if we could do the general n-particle dispersion relation, this would actually enable us to develop the bootstrap program the way that it should have been done in the 1960s, and hopefully connecting up with actual phenomenological amplitudes. So how does this work? So how do you recover this kind of a picture? So this kernel already has this suggestive picture that this is going to be the pole in the S1 variable, this is going to be a pole in the S2 variable, and then this of course does not have any poles, so this can be thought of as a contact diagram. Okay, so how does this picture come about? It's very easy. So let's say lambda is equal to minus S1. You see that the last term and the first term cancels off, and this term I already told you that if lambda is equal to minus S1, it actually simplifies to S1. And this is precisely the fixed S1 dispersion relation. You do the other thing, so this would actually give you the S channel decomposition of the amplitude, or the T channel, depending on, so this will be the T channel decomposition of the amplitude. You do the other case, lambda equal to minus S2, this term and this term cancels, and this is left with S2, and you'll get the other channel decomposition of the amplitude. So this parameter is enabling you to actually interpolate between various pictures. Okay. So this is a kind of a representation where we don't require the full worldsheet picture of string theory to have an interpretation of this kind. I have not talked about a worldsheet interpretation. I don't know if there is a worldsheet interpretation, but I have introduced some parameter which enables me to have the stringy kind of stretching between different channels. So this is what actually leads to this new series representation for the Euler beta function, So this absorptive part is nothing but the discontinuity of the original function. So in the original function, the discontinuity, if you remember, there was this S2 plus n plus 1 Pochhammer n divided by S1 minus n in the series representation. You easily read off the residues, and instead of S2 you replace it by this second argument that is there in the dispersion relation. That is what gives you, instead of S2 plus 1 Pochhammer n, you get this lambda dependent, more complicated dependence on the Pochhammer. This is absolutely vital to have this absolute convergence in the Madhava series, or the lambda version of the Madhava series, simply because n now appears in the denominator rather than in the numerator. So this gives you very fast convergence properties, better convergence properties than what is available in the actual Madhava series. Another thing is that each individual term here, so this part if you summed over n individually, this part if you summed over n individually, this part if you summed over n individually, each converges on its own, and it is absolutely convergent. Each part is absolutely convergent. Okay, it is not as if there is some hidden infinity that that cancels on its own. Okay, so this was the Pochhammer symbol. And this can easily be modified to accommodate different kind of high energy fall-offs. And as I mentioned, this does not need to have worldsheet duality inbuilt. So we have a new way of actually setting up the bootstrap problem, which hopefully is a different way of thinking about how people would have done it in the 1960s. So applications, what would you have done? You can actually revisit the bootstrap problem. So, and you get a space of theories. These various colors corresponds to different kinds of consistent amplitudes only on using tree-level unitarity conditions. So, I have not imposed any nonlinear one-loop level unitarity conditions. I have just imposed tree-level unitarity conditions. This gives you a space of theories. These are some low-energy Wilson coefficients. If you dial and fix the value to the known superstring value, this red triangle here corresponds to string theory. And people have been looking at various kinds of deformations. This black line corresponds to some analytic deformation, which are called hypergeometric deformations. This was done by Mansfield and Spradlin in 24. The blue line here corresponds to theories that are very close in spirit to satisfying worldsheet duality. So blue region is something that would be like old string theory. And one of the motivations for examining the theory space is that we can look for deformations of string theory, and can one of these deformations actually be describing the hadron scattering, which is the original problem that string theory started by attempting to address. And this I'll just briefly mention that when you work on these kind of problems, you worry about the fact that your students need to get jobs. So it's always a good idea to see if somehow one of these modern techniques, machine learning, artificial intelligence, quantum computing somehow is naturally a tool that you can use in your problem. And it turns out that machine learning is actually a natural tool to be thinking about here. And part of the reason is that we can actually think about Regge pole analysis, because machine learning is basically a sophisticated fit function. And in that sophisticated fit function, what it is trying to do is trying to learn a function of two variables, L and N. And the Regge pole tells you that you need to go into the complex L plane and see the poles in the complex L plane. So once you have a complicated fit function, you can actually make that L complex and see where the pole lies. So that is something that is naturally something that you can investigate using machine learning. Another reason why you want to do machine learning is that you can ask that what is so special about string theory? You have a space of now theories. So in that space of theories, why is string theory special? How do you even try to address this question? What rules do you use? Because you don't have a Lagrangian anymore. You're talking in the language of just amplitudes. So then you have to constrain it using physical constraints. So one thing that we looked at is that when you scatter gluons, then the outgoing states actually are entangled. Generically, whenever you have entangled in the helicity space. And so you can ask how much entanglement do these models that I showed you in the scatter plot, in the colored plot, how much entanglement do these models generate? And it turns out that if your spectrum is integer space like string theory, which corresponds to the red line, if you muck up the spectrum, you make it some random spectrum on the real line, then all of them have higher entanglement than string theory. So somehow string theory is the answer to the question which theory generates minimum entanglement in the helicity space in the space of allowed theories allowed by tree level unitarity. So finally, how much time do I have? Oh, I have a lot of time. So anyway, so then we can, let me just pause and ask if there are any questions, because then I'm going to go to the next part, which is going to be Ramanujan's pi.
So what was the access extent down to 0?
Yeah. So this one is just labels the theory. So pth theory.
In your previous color plot also you had.
So okay. So let me just explain the axis here. So here you have you can expand the function of two variables around s equal to 0, t equal to 0. So you write it as w00 plus w10, and then you have to expand in terms of symmetric polynomials. So it's a symmetric polynomials such that it is invariant under st interchange. The building blocks are s plus t and s times t. So w10 would correspond to the coefficient of s plus t. W01 would be the coefficient of s times t. Yeah.
Function that you postulated, if I look at the one loop correction
Yeah.
from theory, how does that postulated function look like?
Yeah, so that's a bit harder to address because you want to actually impose nonlinear unitarity in the bootstrap space, and nonlinear unitarity is right now something that we have not figured out what is the efficient way of imposing that. So let me just explain a little bit why that is true. So you see, so there is a version, a more general version in terms of the partial wave expansion, where you see the Gegenbauer polynomials and the partial wave coefficients sitting that arises from the dispersion relation. Now there is going to be a lambda dependence in that formula. So the one of the consistency conditions is that the final amplitude does not depend on lambda. So you'll have to actually demand lambda independence, and on top of that you have to also demand unitarity, tree level unitarity, and in the question that you're asking, one loop unitarity. So you have to impose both of them.
I mean, do you know it will exist?
Which one?
The function that you postulated.
Yes.
Okay.
Yeah.
Will it exist?
You mean the dispersion relation itself, will it exist? Whether this exists
For the
non-perturbatively?
function.
Yeah. So whatever we have tested, so you can take any one loop amplitude or even two loop amplitude that you, standard results for colored scalars, for example. Colored scalars are somewhat simpler. You can do it for gluons, but let's ignore that. I mean, for colored scalars, whatever we have tested, this works. So at least perturbative level,
It works.
it works. So this lambda somehow is there in the channels, but when you add everything together, it drops out. Yeah. Best. So best in what sense? Just are you talking in the say what is the best value of lambda that you can use? So that is an excellent question. So okay. So expanding that amplitude, are you talking about low energy expansion or are you talking about this lambda dependence? Which one are you talking about? The low energy expansion. So low energy expansion is something that is from the Wilsonian spirit, that when you are actually, so you have some low energy spectrum, so you want to see those show up in the amplitudes, and then you want to add non-renormalizable terms in your theory, in the Lagrangian description. So the Wilsonian coefficients are just the coefficients in front of those non-renormalizable terms. So you would actually expand around the, so in the case of gluons, you would expand around the massless pole. So the massless pole plus you want to see a polynomials. So this is the way that you would actually, so what this means is that in the language of Lagrangians, you would actually get something that is f square, and then you would get these higher derivative corrections involving f. Okay, so you, so if you expand around s equal to 0 or t equal to 0, the building block now just becomes f, the gluon field strength.
Yeah, I have one thing. Like, so you are taking the same amplitude and decomposing in different ways, right?
Yes.
So so let's say if I start from string theory and if I decompose as string field theory, decompose the amplitude, one advantage is that at any loop I can control the renormalization, right?
Yes.
So this way of decomposing, will it allow you to even address the renormalization problem?
Well, yeah, I mean, since I've written down a dispersion relation, so the only things that writing down this dispersion relation needs are high energy fall-offs. So we can, so this actually, I should actually tell you that this works for high energy fall-offs that are worse than string theory. So let's say that your amplitude behaves like s to the power t, okay. That is how string theory amplitudes typically behave like. But in order for this to work, your t will get replaced by this, okay. T gets replaced by something that morally looks like 1 over sigma. And in the sigma going to infinity limit, it converges very well everywhere, not just for t negative, it converges everywhere. Does that make sense? So
Yeah.
So in fact, so just to put that in context, suppose you had an amplitude that went like s to the power t square. Okay, this is not something that we see in string theory, but this dispersion relation will still be able to accommodate that amplitude simply because that t square is going to be replaced by 1 over sigma square, and in the sigma going to infinity limit, the integrand will still converge.
Okay, thank you.
Are you suggesting lambda itself could be the renormalization parameter?
Yes, in fact that is a good way of thinking about it. In fact, I tried to sell lambda as some kind of an elasticity parameter, but there is another way of thinking about lambda, which is in the language that you are saying. So imagine that you have some low energy particles and then you have a tower of high energy particles, and then you truncate that spectrum, and then you perform a field redefinition of the fields that you threw away. That will show up in the contact terms in terms of the low energy fields. So that's another way of thinking about the lambda parameterization. Yeah.
Any comment on the positivity properties of A?
So that's a very good, so unfortunately I haven't shown you the plots. You get this positivity structure if you use the fixed T dispersion relation. This actually gives you an enhanced positivity domain. So the full amplitude has definite sign definiteness in a bigger domain than what the fixed T dispersion relation allows you.
Okay, there is one question from online. Can you
Yeah.
constrain multi-loop amplitudes to one loop or two loop amplitudes so we can modify this postulated formula to find its general case? Not sure.
Yeah, so I guess the question is related to generalized unitarity at the level of dispersion relation. So this is something that we have not looked at, but definitely, hopefully we'll.
Please go ahead, yeah.
Yes.
Yeah,
There was
so
something else,
a naive question. So in one of your earlier slides, so you showed the two values of lambda, right? And then there was some
Yeah.
decisions, right?
Yeah.
So how do you actually choose lambda? Like,
Very good question.
Yeah.
So, since you asked this question, I'm glad that you asked this question. So, yeah. So your question was, so let's restrict to pi and ask, if I truncate at n, what is the best value of lambda to choose? Okay. So this is a plot generated by my new graduate student CGPT the 5th, and so this actually suggests, and it was very convincing, and CGPT's personality is very different from the earlier models. It is actually very insistent. It tries to actually reverse brainwash you, so that whatever it is saying is correct. It's a kind of a dangerous model. So, but you can verify because I checked what it is saying anyway. So the optimum value, so this is when you're truncating, optimum value lambda star actually seems to lie on a straight line, approximately a straight line. So you want to choose lambda star to be approximately n max.
nice.
And it's an intriguing thing. Trying to find an analytic answer to that is, I think, very hard, even at the level of pi.
Thank you.
Finite size scaling argument.
Yeah. So no, thank you has not come as yet. Okay. Okay, so let's continue. So the last part I'm going to talk about Ramanujan's pi and physics. And this is, it's a freely available paper. If you just search for Ramanujan's pi 1914, you can download the PDF. And I tell you, I had an emotional reaction reading that paper, and that emotional reaction stemmed from the fact that I didn't understand anything. The first 2 pages made me cry because I thought that I knew nothing. Okay, because he just quotes formulas. It quotes formulas using complete elliptic integrals of the first kind and so on, just writes down the modular equations and so on. And one of the famous formulas that is quoted again and again, if you just do Google and ask what is the famous Ramanujan 1 over pi formula, you're going to see this. Okay. And we want to understand where these come from, at least get some kind of a feeling. Maybe we won't reach the final answer, but we want to understand where these things come from. And as I said, that this part, I don't have a clear motivation. I am just driven by curiosity. I want to understand, is there a physics connection, some physics story, interesting physics story to say about the origins of these formulas. So here is Ramanujan. This is Ramanujan in 1914. So Ramanujan's 1914 paper is devoid of algebraic details. And the story goes that he wanted to conserve paper as he could not afford it. So all the intermediate steps were on a slate. I asked my student to make a cartoon, and I told it that draw a picture of Ramanujan sitting under sitting under a lamp, working on a slate with a chalk. This is what it came up with, and now disturbingly, it seems like he's working on an iPad rather than a slate. So, but apart from that, it seems like a decent representation. Yeah. So what is the starting point of Ramanujan's formulas? And this is mathematically very dense, but it's very interesting. The starting point is something called the Legendre relation. Okay? So if any of you are familiar with the mathematics of complete elliptic integrals of the first and second kinds, there's a relation between them which roughly speaking takes on the following form. So there's a combination of k and e. So the standard notation that you'll find in Ramanujan's papers are k and e. They are nothing but special kinds of 2f1 hypergeometric functions, and the relation can be actually rewritten in terms of derivatives of the hypergeometric functions of this kind. Okay? So there are the starting point, what you should remember, take away from this formula is that it's a product of 2 2f1s. Anybody who has ever read the big fat yellow book on conformal field theory, sorry? 2f1 I have suppressed the arguments, I will show you. It is there. The arguments are sigma, 1 minus sigma, 1, and then there are 2 arguments, z and z prime. I have set z equal to z prime after doing the derivatives. Yeah. Now, anybody who has read this big fat yellow book, again a kind of a dumbbell, but it is encyclopedic, it's very nice. I mean, this is something that I think most graduate students working in string theory related areas would have been forced to read by their sadistic advisors here. So we'll immediately jump at the fact that the product of 2f1s, I've seen these appear in conformal field theories. What kind of conformal field theories? So now you have to address the question, where do these 2f1s appear? Can you identify this structure 2f1 times 2f1 as a particular conformal correlator, a 4-point correlator? This is what we are usually familiar with in conformal field theories. And then identify what theories give rise to those correlators. Okay. The other question is that, okay, I'm taking the derivative, there is a z dependence, and lo and behold, in spite of this z dependence, this is a constant. Is there a physics way of understanding that? Okay, and the physics way, of course, you have to do something, so there is some ADS-CFT hokey pokey going on here. And in the ADS-CFT language, there is something that we know which is called the membrane paradigm. When we calculate transport coefficients, when we calculate the famous ratio eta over S, there is a way to actually do the calculation properly by placing the boundary at infinity, but there is also a way of doing the calculations by calculating objects on the horizon. So this membrane paradigm enables us to calculate transport coefficients by just examining horizon physics. And the physics reason for this constancy of the left-hand side is because of this membrane paradigm. These transport coefficients can be obtained by evaluating on the membrane approximation to the black hole horizon. So now this understanding, this new understanding that we are getting pointed at, first of all requires us to understand what kind of log CFT enters, and whether this log CFT enables us to get a new efficient handle On the next step, so this is not enough to get 1 over pi. So you see, you have 1 over pi on the right hand side. What Ramanujan would have done, or what Ramanujan did in his paper, is to actually find efficient series representation of the left hand side. You have product of two F1s. In the Ramanujan formulas, you only saw one sum. The first thing that you would be tempted to do is decompose the two F1s into sums. And then you would get a double sum. That is useless. Okay? That is not where the Ramanujan's cleverness originated. Ramanujan's cleverness originated in identifying what are called singular values, which in order to define singular values, you have to define what are called modular equations. So modular equations are special slices. So this is a function of two variables. It's a conformal correlator. It's a function of two variables, z and z bar. You have to take special slices, z bar as a function of z, and then take the diagonal limit along those slices. Those are called singular values, and Ramanujan was able to calculate the singular values on his slate. And these take on absurdly long forms, square root of big numbers and so on and so forth, nested square roots and so on and so forth. And how he came up with them just by calculating things on a slate is anybody's guess. Nobody is able to recreate the final formula that was there in his paper analytically. I mean, there are alternative indications, calculations using Maple or whatever, Mathematica, but how he did it by hand is nobody knows. So here is the flow chart, and where the stringy dispersion relation in the previous part actually plays a role. So first of all, we need to identify the 2f1 times 2f1 structure, and it turns out that this is actually associated with the log CFT correlator. Later on, if anybody is interested in conformal field theories, I can explain how this originates. And next step is that to notice that it has the same crossing symmetry, this permutation symmetry. It's a function of two variables, but now in the position space. It's not in the momentum space like Veneziano's amplitude. But you can still use the same stringy dispersion relation, and the advantage that you get is you get a new kind of basis, a new kind of log CFT blocks. And these new kind of log CFT blocks exhibit very rapid convergence in the sum over the spectrum. The Legendre relation that I showed you, where you have 1 over pi on the right hand side, remarkably, in order to decompose this correlator, you only require to keep the log identity operator. All the other towers of identity operators contribute 0. The log identity operator contributes everything. And then because of this approximation, you can now have a new approximate handle, a conformal field theory handle, on these very difficult modular equations. So just to give you an idea of these modular equations, you take a slice. So this is z and z bar. I told you the correlator is a function of two variables. Z equal to z bar is the simplest modular equation. Then these become more and more complicated. I won't go into the details about how these are obtained. But Ramanujan would have analytically found along this diagonal line the values of what are marked by x. Okay. Why it was important is that these x's have algebraic expressions. By algebraic expressions means things that satisfy algebraic equations. These are not transcendental numbers. Because imagine that you had a formula for pi which had zeta 3 in it. It would be useless because zeta 3 is transcendental, and you require to actually have a new algorithm to calculate zeta 3 itself. So you require to have an algebraic way of calculating pi. And now is the last part. This is ongoing, and this is something that I don't really have a clear idea except for some suggestions. So suppose you started off with the static patch of de Sitter space. Hubble scale this. You write down the static patch like this. You solve the Klein-Gordon equation. Simple enough. My new student can do it. And the mass of the scalar field in the Klein-Gordon equation is related to sigma times 1 minus sigma. There are two solutions. This is a hypergeometric equation. There are two solutions, and the Green's function on the static patch, which is regular at opposite horizons, is precisely the starting point of the Legendre equation. So this is precisely of the same form as the correlator that goes in. So this seems to suggest that there might be an interesting reinterpretation of all these very complicated mathematics that went into Ramanujan's pi, modular equations and so on and so forth, in the language of maybe the double scaled SYK or something like that. So the outlook is sometimes it is physics that provides the guiding light, like the first part of my talk, which was motivated by the question, can we come up with a better version of string theory? Since after all, as we learned beautifully in Sandeep's review, in spite of its magnificent glory, it is useless so far as nature is concerned. Sometimes it is the mathematics that provides the guiding light. Maybe it will tell us how to do the bootstrap program better or something. Also, purely from the mathematics point of view, is there a connection with the Langlands program? Because the moment you see number theory, you begin to wonder if there is an underlying overarching unifying picture, and that goes by the name of the Langlands program. But let me just spend the last 2 minutes giving you some gyan. So one of my heroes is Paul Dirac. Dirac came up with his famous equation in 1928. 3 years down the line, it will be 100 years of Dirac equation. This Dirac equation predicted antiparticles. Bhabha scattering is named after him. From 1928, the first commercial positron emission tomography, which is based on the existence of the positron, this commercial application was developed in 1973, so like 45 years. So I'm absolutely confident Dirac wouldn't have been able to predict this commercial application, the application to medicine. And of course you have heard of Dirac-Cohen graphene and so on and so forth. He got the Nobel Prize, and you would have thought that, oh, Dirac must have been a very happy person, very happy in the modern Gen Z language, very happy dude towards the end of his life. I can safely say that was not the case. Dirac was a very taciturn person. There is a YouTube video. This person is Hund, the person responsible for torturing us in chemistry in class 11 and 12. And he gives an interview to Hund. This is available on YouTube. It's around a 20-minute interview. Around minute 18, Dirac launches into a tirade against quantum field theory. Okay. So Dirac, sorry. So Dirac, in spite of being one of the originators of quantum mechanics, quantum field theory, had a very negative view of his own creation. So in fact, in 1970s, Dirac in an interview said, the present form of quantum mechanics should not be considered as the final form. It is the best one can do up till now, but one should not suppose that it will survive indefinitely into the future. And I think it is quite likely that at some future time, we may get an improved quantum mechanics in which there will be a return to determinism, which will therefore justify the Einsteinian point of view. Now this is a controversial point of view. People seem to say that hidden variables are ruled out and so on and so forth. But who knows, maybe there's a creative way of getting around those as well. But what actually really gobsmacked me was reading Dirac's biography, a beautiful biography by Graham Farmelo. And so in this biography, the story goes that there's this famous string theorist by the name of Pierre Ramond. Ramond Flux you heard in Sandeep's talks, the same Pierre Ramond, who worked with, who was a student of A.P. Balachandran, who was a frequent visitor to Max Science. And it goes that Ramond went to invite Dirac, and this is when Dirac had moved from Cambridge to Florida. Ramond had gone to invite him for a colloquium, and Dirac said that, no, I have nothing to talk about. He said, my life has been a failure. And it goes, Ramond would have been less stunned if Dirac had smashed him over the head with a baseball bat. Dirac explained himself without emotion. Quantum mechanics, once so promising to him, had ended up unable even to give a proper account of something as simple as an electron interacting with a photon. Calculations ended up with meaningless results full of infinities. These are all ultraviolet infinities, and string theory, as you heard in the morning, has the promise of being able to deal with these ultraviolet infinities, although we have not made connection with exactly this problem. But this was the cause of his sorrow. And also one of the challenges that he actually posed, and this is in the spirit of the standard model table that Sandeep showed in his talk. Dirac famously asked, why is alpha 1 over 137, at least at low energies? So is there some fundamental reason for these numbers? So I'll stop there, and thank you for your attention.
Okay, thank you, Anindya. Are there any questions for him?
Thanks for this very insightful talk. So I was just wondering, like, you gave an interpretation of lambda with regard to string theory and all, but you also said like it has some sort of elastic. Are there any classical benchmarks for this? Have people thought about it, or there are some results somewhere out there?
What do you mean by
But
classical
like,
benchmarks?
yeah, because
Devoid
the-
of...
finally the expression essentially is a
Yeah.
mathematical identity.
Yeah,
right?
yeah.
And the interpretation is up to us
Yeah.
to make.
Yeah.
So, and you gave us one interpretation today.
Yeah, so to the best of my understanding, nobody has come up with any alternative classical interpretation. I guess from the mathematics point of view of what this parameter makes. So if you go to through Rosengren's proof, so the proof that I presented channeled dispersion relations in some way. Rosengren's proof uses standard methods of partial fractions, and he has some interesting ways of actually building in lambda. He says that it is related to removing or making the series converge at infinity. So there is some high in my language, his way of looking at it would correspond to some high energy behavior of this series. So there is a convergence kind of argument that he gives. So maybe that is the closest that I can tell you. Yeah.
Okay. Thanks again.
Other questions or comments?
4-point formula, can you I mean, is there such a formula for 5 or 6 point?
Yeah, so that is what. So the 5-particle dispersion relation, there is no understanding of 5-particle dispersion relations or any useful understanding of 5-particle dispersion relations in the history of quantum field theory so far. So one has to build it up from scratch. So we have some ideas, at least for color ordered amplitudes, we have some ideas. There was a proposal that was there in this paper that I flashed. The complication there is roughly as follows. So in the 5-particle case, we actually require 2 dispersive variables, at least 2 dispersive variables. Because in the 5-particle case, you can have a cubic vertex or a quartic vertex joining with a cubic vertex at tree level. So you will require 2 variables because there are 2 discontinuities in the cubic vertex language and then 1 discontinuity in the quartic cubic gluing language. So the challenge there is that in the 2 variable case, when I actually want to make it symmetric, I will have a Jacobian of the transformation, and that Jacobian actually is a determinant. It has a complicated form. So we got away with it in the 2-to-2 scattering case because the Jacobian was simply a derivative. It was we got an ordinary differential equation, which was very easy to solve, which is what gave us this complicated looking second factor in the absorptive part.
Okay.
So this decomposing of this to scattering amplitude in string theory, like basically we are just decomposing the moduli space of,
Absolutely, yes.
right? So is there any way you could do the decomposition of moduli space and identify each term in your expansion?
Yeah, that's a very good question. So I've asked this to experts. And so I would love to know if there is a way to get from string field theory this formula that we have.
You can decompose it like
But it won't be similar. So the way that you would naively do, this is building on Ashok's work, is that you would actually isolate the points in the moduli space which give rise to the poles and surround them with a circle, and the boundary term of the circles is what you would give rise to the pole part. And then there would be a region which actually excludes these points where you have singular values, and you have to integrate over that region. The complication is that suppose you are doing it, let's say you are doing it for the closed string. So in the closed string, you will have the S-channel pole and the T-channel pole. So, so basically you would require to have, you need to know a conformal transformation that actually takes this cut picture and maps it into concentric circles. And this conformal transformation to map it into concentric circles is not known. So that is why you'll have to do this integral, which is finite, which corresponds to the contact term numerically. If there was a clever way of actually sort of expanding this conformal transformation analytically, then maybe there is a way to actually do what you are suggesting analytically.
Thank you. So maybe one more thing. Maybe Alok is there, maybe he knows. So there are this different way of decomposing the amplitude, like let's say using this positive geometry.
Yeah.
So will this expansion has any correspondence there?
Yeah, this is a very good question. So the 2 comments. So in the string theory analysis that Nima and others have done, they have come up with a version or a way to understand the 5-particle amplitude in the same sense that we understand the 2-to-2 scattering in the language of gamma functions. So you start out with the worldsheet integral, and then you do analytic continuation, come up with a formula that is convergent everywhere except at the poles. Okay, so that part is done. Okay. Now, what is not understood is how to write down or how to do a series expansion of the final formula, which has this structure that you have the poles, and the poles talk to each other if you are looking at it in the language of cubic vertices or in the language of cubic quartic gluing, you have a single cut. So that decomposition is not known. So that is still pending. The second comment I wanted to make is that in the amplitudes program, they have these beautiful results where you have, you are in some sense, you have a control over the integrand. But in order to calculate a useful number, you still have to do the integrations, and the integrations will require you to add counter terms. And it is still not understood what kind of positivity role those counter terms play. Now imagine that you were able to do it in the language of dispersion relations. You would not require to know any of these counter terms. So that could be, that is why I think understanding the language of dispersion relations may be fruitful in that sense as well.
Thank you.
Okay, okay, one last question.
You mentioned that there is this strong influence of mathematics on physics and vice versa. Do you, for instance, interact with the maths department in your institute?
Yeah. So.
And how strong is that interaction? Has it led to something very useful?
So okay, since you asked this question, let me explain to you so once we actually had our, yeah, it's fine. Nothing controversial, don't worry. So I sent my paper to, because our divisional chairman and director are both mathematicians. So I sent, because I felt that, they might be interested in these kind of new series. So they both were very encouraging. And in fact, the divisional chairman sent the press person to my office to talk to me. The press person said that I don't understand your paper. So the only formula that seems interesting is this pi formula. Maybe we can make a story out of this. So that was that was how it originated. Now there are also mathematicians that I wanted to actually send this to, Apurva Khare being one of them, in our institute, and he sent it to Terence Tao. The paper he sent it to Terry Tao because Terry Tao is known to him, and he asked him whether he had seen these kind of series representations. And Terry was very conservative in his reply. This is what Apurva told me. I didn't see his email, but Apurva told me that he said that but pi has been studied for such a long time. Maybe it is hidden somewhere, so we really can't say. The other person that I actually talked to is my colleague in Calgary, who actually works on the Langlands program. And the conversation actually usually goes, we are very excited to see each other. He talks in the language of Adels and number theory and p-adic numbers and so on and so forth. I talk in the language of whatever rudimentary mathematics that I know. So he doesn't understand the physics that I'm talking about. I don't understand the maths that we are talking about, but there is some connection there at a level that we still don't understand. So we keep talking to each other still.
Okay, I think it's last, very last, after this break for lunch.
Sorry, this is the second part of your talk, which is, in a sense, Ramanujan's expansion of 1 over pi is regarded as one of the fastest converging, right? But has it been improved since?
Yes, so the Chudnovsky algorithm, which gave to even faster converging series representations, were built on or were motivated by this Ramanujan pi series. I mean, so the world record, I told you 200 trillion digits are is the world record. That actually uses these kind of Ramanujan motivated algorithms.
I see. But is it just this much, and then tell me, is it based on hypergeometric functions and their properties, or is it a complete
modular forms? There are some modular forms that enter the story. Yeah.
Thank you.
Okay, let's thank Anindya for a very nice talk. And we'll meet at 2 o'clock.